Here is the periodic table in its current form. We need to become comfortable with using it, so let's look at all the information that it contains. Each cell in the periodic table contains information for a single chemical element. Let's look at the cell for magnesium. The atomic number, that is the number of protons in the atomic nucleus for the element, is typically shown in the upper left corner of the cell. For magnesium, it is 12. The cell will also always contain the chemical symbol for the element. The chemical symbol consists of one or two letters, typically abbreviating the English or Latin name of the element. The first letter is capital. For magnesium, the chemical symbol is Mg. Many but not all periodic tables will also include the complete name of the chemical element. Below the chemical symbol and the name of the element is the value of the atomic mass. This value is given in atomic mass units, abbreviated as AMU. The atomic mass unit is roughly equal to the mass of a proton or a neutron, and it is about 1.66 times 10 to the minus 27th power kilogram. For magnesium, the atomic mass is 24.305 atomic mass units. The background color of the cell in the periodic table or the font color of the chemical symbol of an element may be used to color code some information about the properties of the element. Such color coding varies between different editions of the periodic table and may be absent altogether. Other information, such as the electron configuration, is sometimes included in periodic tables. As we said in the previous video, the elements that are in the same column or group in the periodic table have similar chemical properties. The elements in neighboring cells of the same row or period in the periodic table have similar atomic sizes. The groups in the periodic table are numbered from 1 to 18. Some editions of the periodic table may also include an alternative, older notation for numbering the groups that includes an Arabic or Roman numeral and a letter, A or B. We will not be using this notation in our class. The periods in the periodic table are numbered from 1 to 7. The elements in the periodic table can be classified in several different ways. First, let's consider the following classification. This classification is based on the electron configurations of atoms. If we were to write out the electron configurations for all atoms, as we have done for the first 11 and strontium in a previous video, we would see that for atoms in the first two groups and for helium, we would be adding the last electron to an s subshell. For hydrogen and helium, we would be filling the 1s subshell. For lithium and beryllium, the 2s subshell. For sodium and magnesium, the 3s subshell, and so on. Collectively, we will refer to these elements as the s block. When writing the electron configurations for elements in groups 13 through 18, except helium, we would be adding the last electron to a p subshell. For the elements in the second period, boron through neon, we would be adding electrons to the 2p subshell. For elements in the third period, aluminum through argon, it would be the 3p subshell. For elements in the fourth period, gallium through krypton, it would be the 4p subshell, and so on. Collectively, we will refer to these elements as the p block. Between the s block and the p block, we find elements that belong to the d block. As you hopefully remember from the video on electron configurations, after we have entirely filled the 3p subshell, this occurs for argon, the element whose neutral atom has 18 electrons, and the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. We start filling the 4s subshell, where electrons have the next lowest energy. We are adding electrons to this subshell for potassium, atomic number 19, and calcium, atomic number 20. For the next 10 elements in the fourth period, scandium through zinc, atomic numbers 21 through 30, we are adding electrons to the 3d subshell. Similarly, for elements with atomic numbers 39 through 48, yttrium through cadmium, we are adding electrons to the 4d subshell, and so on. Collectively, all elements with a lost electron in the electron configuration is added to a d subshell are referred to as the d block. Finally, for elements with atomic numbers between 58 and 71, and those with atomic numbers between 90 and 103, the lost electron in the electron configuration is added to the 4f and 5f subshells respectively. These elements are collectively referred to as the F block. Often the F block elements are shown separately at the bottom of the periodic table. It is done primarily for typographic reasons. The elements for which we are filling the 4f subshell should be placed between elements with atomic number 57, lanthanum, and 72, hafnium. And the elements for which we are filling the 5f subshell should be placed between elements with atomic number 59, actinium, and 104, rutherfordium. However, such an arrangement makes the 6th and 7th periods of the periodic table very long visually. So these elements are usually shown separately at the bottom of the periodic table instead. We will not be discussing these heavy elements in this class. By looking at the S, P, D, and F blocks in the periodic table, we can realize that a new period begins once the S and P subshells of a shell have been fully occupied by electrons. The exception to this rule is the first period that only consists of two elements, hydrogen and helium. As you may remember, the first shell only has an S subshell, no P subshell. The first period in the periodic table ends when the first shell is completely filled with electrons. All elements in group 18 of the periodic table, except helium, have 8 electrons in the shell with the largest principal quantum number that contains any electrons. For helium, the first shell is completely filled by its 2 electrons. The elements in group 18 are gases, and their atoms do not readily combine with other atoms. We call these elements the noble gases. The electron configurations, particularly for elements with larger atomic numbers that have more electrons, may get quite long when we write them out explicitly. In the video on electron configurations, we have written out the electron configuration for strontium, atomic number 38, and it was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Imagine writing out the electron configuration for a heavier element, like uranium, atomic number 92. Fortunately, as we will learn in the second part of this course, only electrons beyond the ones that comprise the electron configuration of the last noble gas that precedes a given element play any role in how atoms of that element can connect with other atoms. For instance, for strontium, the first 36 electrons are arranged in the same way as for krypton, atomic number 36, the last noble gas that precedes it. The electron configuration of krypton is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. with 2 electrons in the 4s subshell and 6 electrons in the 4p subshell, for a total of 8 electrons in the shell with the largest principal quantum number, 4, as is the signature of noble gases. Therefore, only the 2 electrons in the 5s subshell will determine the chemical properties of strontium. Because of this, electron configurations are often written in shorthand form. They start with the chemical symbol of the last noble gas that precedes the element in square brackets, followed by the electron configuration for any electrons beyond those present in the noble gas written out explicitly. The chemical symbol of a noble gas in square brackets is shorthand 4. The electron configuration is the same as for the last preceding noble gas, with the configuration for any electrons beyond those present in the noble gas written out explicitly. For strontium, the electron configuration can be written in shorthand form as follows. Krypton, in square brackets, 5s2, meaning that the first 36 electrons are arranged in the orbitals in the same way as in krypton, and there are 2 additional electrons in the 5s subshell. Let's consider a couple more examples. For lithium, atomic number 3, the last preceding noble gas is helium. Therefore, in shorthand notation, the electron configuration of lithium is written as helium in square brackets 2s1. The first 2 electrons are in the 1s subshell, as in helium, and the third electron not present in helium is in the 2s subshell. For phosphorus, atomic number 15, the last preceding noble gas is neon. Therefore, in shorthand notation, the electron configuration of phosphorus is written as neon in square brackets 3s2, 3p3. The first 10 electrons have the same configuration as in neon, 1s2, 2s2, 2p6, and the next 5 electrons not present in neon are distributed as follows. 2 completely fill the 3s subshell, and 3 occupy the 3p subshell. Note that in this notation, the chemical symbol in square brackets is always that of the last noble gas that precedes the chemical element. Electrons in subshells beyond those filled in the electron configuration for the last preceding noble gas are called valence electrons. These electrons are very important in chemistry, and we always write out the electron configuration for valence electrons explicitly. We will be talking a lot more about valence electrons later in the class. All electrons in an atom except the valence electrons are called core electrons. Their significance in chemistry is much more limited.